Guido Imbens was born in 1963 in the Netherlands. He received his PhD in 1991 from Brown University, Providence, USA. He is the applied econometrics professor and professor of economics at Stanford University, USA. So please welcome Guido.
I want to thank the committee for the prize, and in particular for highlighting the importance of credible causal inference. The estimation of causal effects, comparisons of outcomes under different treatments or policies from observational, non-randomized data, is important for providing advice to policymakers. In the last 3 decades, there's been an explosion of work in this area in economics as well as many other disciplines, and I see the prize as a recognition for all of this work. I grew up in a small town in the Netherlands. While in high school, I was faced with the decision what major to choose for college. My economics teacher lent me a book by the 1969 Nobel Laureate and Dutch econometrician Jan Tinbergen, which appealed to me with its mixture of mathematics and practical relevance. I was particularly impressed with Tinbergen's ability to combine high-level academic work with involvement in policy advice, and I decided to enroll in the econometrics program in Rotterdam that Tinbergen had founded in the 1960s. After a detour through an exchange program with the University of Hull, I did my PhD at Brown University in the US. Since then, I've moved around from coast to coast before settling in 2012 at Stanford University in California. During my undergraduate and graduate days, I was not exposed to much work that explicitly focused on causality. Although there had been case studies going back as far as the 1860s, including the Snow study on the causes of cholera, and econometrics has implicitly always focused on causality, the explicit use of the term causality was rare through the 1980s and early 90s. It only started increasing sharply after 1995, with currently over 50% of working papers in the National Bureau of Economic Research working paper series using the term, as the figure on the right, based on the work by Curry, Cleven and Sveriges, shows. Looking back at my own work from that time, Josh and I did not use the term causal in our 1994 paper on the local average treatment effect, but 2 years later used it over 100 times in our 1996 paper with Donald Rubin. Nowadays, causal inference is a fast-growing, vibrant and interdisciplinary field with researchers in statistics, political science, economics, computer science, epidemiology and other areas working on common problems, coming from different perspectives with different tools, and interacting closely in conferences and seminars. During the pandemic, I started, together with other researchers in this area, an online inter-university seminar on causal inference that weekly attracts hundreds of attendees. In the last year, a Society for Causal Inference has been founded to further bring together this community. To put the themes of this talk in context, let me start by being clear about what I mean by some key terms. The way I want to think about causality, and this is heavily influenced by the work of Donald Rubin, is in terms of effects of manipulations or interventions. A unit, say an individual or a firm or a country, can be exposed to some policy or intervention at a particular point in time. For example, an individual can take or not take some medication, or a country can enact or not enact a lockdown or mask mandate to combat COVID-19. We can see what the unit did, take the medication or not, enact a lockdown or not, and we can see the outcome given that action. What we're interested in is the comparison of the actual outcome with the counterfactual outcome had the alternative action been taken. The comparison of the actual outcome and the counterfactual is the causal effect. We cannot ever measure such a causal effect directly because we cannot see the counterfactual outcome. A randomized experiment solves a big part of the problem. I take a population of units and randomly assign some to the intervention or treatment and the others to the alternative, the control treatment. The randomization ensures balance, at least in expectation, ensuring we can estimate at least the average causal effect under weak assumptions. In economics and other social sciences, experiments are often not feasible, and we have to make do with observational studies where assignment to the treatment or control group is partly the result of deliberate choices rather than purely chance. As a result, there may be confounders, that is, variables that differ between the treatment and control groups and that may be correlated with the outcomes directly. Their presence makes it more challenging to credibly infer causal effects from observational data, especially if some of the confounders are not observed. With natural experiments, we try to get back to the credibility of randomized experiments, without formal randomization. I cannot say it better than my 10-year-old daughter said it to the Stanford media team on the morning of October 11th. Doing experiments without really doing experiments. In practice, it turns out that there are many cases where idiosyncrasies in the assignment process create such natural experiments that allow for credible causal inference. Policy decision and regulations often involve arbitrary cutoffs, and small changes in one's environment may lead to substantial changes in actions, as behavioral economists have shown in many settings.
Let me start with a very brief history of causality in econometrics and statistics as far as it relates to our work on natural experiments and instrumental variables. In the 19th century, there were some interesting case studies. In particular, one could make a case for viewing John Snow as the patron saint of natural experiments for a study demonstrating the role contaminated water played in the spread of cholera. In the 1920s and 30s, Fisher and Neyman developed statistical methods for designing and analyzing randomized experiments. This work was hugely influential, in particular in biomedical settings. Randomized experiments are still widely viewed as the gold standard in causal inference. Eventually, in 1962, US Congress mandated the use of randomized experiments for assessing the efficacy of new drugs. Currently, experiments are also widely used in online settings by the tech companies and by development economists, including the 2019 Nobel laureates Banerjee, Duflo, and Kramer. Whereas statisticians emphasize the chance aspect of the assignment mechanism in randomized experiments, econometricians during the 1920s to 40s focused on problems where choice by economic agents played a primary role. Tinbergen studied the demand and supply for goods in agricultural markets using data on quantities, prices, and other variables. Prices are obviously not set randomly in such markets, and Tinbergen used instrumental variables ideas to estimate the demand and supply functions. Sewell, Wright, and Tinbergen also used graphs to illustrate their models in an approach that in the 1990s and 2000s was rejuvenated and formalized by Judea Pearl and co-authors. Havelmo studied the relation between consumption and income. He described the consumption function as a theoretical concept defined in terms of controlled experiments of the type Neyman and Fisher considered. Like Tinbergen in a different setting, Havelmo is very careful in articulating the difficulties in estimating the consumption function that arise from income being determined by the same forces that determine consumption, rather than being randomly assigned. In the late 1960s and 70s, statisticians ventured beyond randomized experiments in their studies of causal effects. In particular, Don Rubin extended the Neyman setup for randomized experiments to observational studies using a potential outcome setup in combination with an emphasis on manipulation to define causal effects. Around the same time, extending the line of work by Tinbergen and Havelmo, econometricians associated with the Coles Commission built increasingly complex models, diverging from the experimental approach in statistics. Over time, statisticians became increasingly suspicious of the simultaneous equations models used in econometrics. Phil David, for example, wrote, "I despair of ever understanding the logic of simultaneous equations well enough to tackle them."
The increasingly technical nature of this work also led to growing skepticism among some econometricians and a concern of a widening gulf between theoretical econometricians and researchers doing empirical work. In a paper with the title, "Let's Take the Con Out of Econometrics," Ed Leamer bemoaned that the credibility of empirical work was at a low. He wrote that, "This is a sad and decidedly unscientific state of affairs we find ourselves in. Hardly anyone takes data analysis seriously. Or perhaps more accurately, hardly anyone takes anyone else's data analysis seriously." To improve the credibility of empirical work, or at least to be clear about its limitations, Leamer suggested making sensitivity analysis a more routine part of empirical work. Much interesting work has been done in this direction, including recent work by Andrews, Jenskow, and Shapiro, and it continues to be a very active area, with additional impetus from the work on partial identification initiated by Mansky. It has so far not become as routine a part of empirical work as Leamer might have hoped, or as it should be. David Henry also questioned the credentials of econometrics in a paper with the title, "Econometrics, Alchemy or Science?" His conclusion is more optimistic than Leamer's, though, arguing that the ease with which spurious results could be created suggested alchemy, but the scientific status of econometrics was illustrated by showing that such deceptions are testable. Around the same time Leamer and Henry argued their case in general, Lalonde demonstrated the lack of credibility of popular econometric methods convincingly in a very specific setting. Lalonde took data from an experimental evaluation of a job training program. The program was effective, with a precisely estimated effect on subsequent earnings. Lalonde then put aside the control group from the randomized experiment and tried to replicate the results with various non-experimental comparison groups constructed from public use surveys, using a variety of state-of-the-art econometric methods. He concluded the methods did not deliver the goods. In his abstract, Lalonde wrote that this comparison of experimental and observational methods shows that many of the econometric procedures do not replicate the experimentally determined results. And it suggests that researchers should be aware of the potential for specification errors in other non-experimental evaluations. Followed by the recommendation in the conclusion that policymakers should be aware that the available non-experimental evaluations of employment and training programs may contain large and unknown biases resulting from specification errors. Lalonde's paper was very influential, and it led Congress to insist on the inclusion of experimental evaluation components in many labor market programs. It was part of the inspiration for the work by Abhijit Banerjee, Esther Duflo, and Michael Kramer that made experimentation a regular tool in the Development Economists Toolkit, leading to their Nobel Prize in 2019. It also led to much theoretical work on better methods involving matching and propensity score methods that have lessened some of Lalonde's concerns. However, the Princeton Labor Group, led by Orly Aschenfelter, took a different route that was not suggested, explicitly or implicitly, in the Leamer, Henry, and Lalonde papers. In what Josh and Steve Piska later called the credibility revolution, they focused on applications and methods that led to results that were believable, and that not just the authors, but also other researchers and policymakers would take seriously, without being based on explicit randomization in controlled experiments. Well-known examples of such natural experiments include many of the papers referenced in this year's prize citation: the Angeris Veterans paper, the Card-Mariel Boatlift paper, the Card and Kruger minimum wage study, the Angeris and Kruger education paper, but also the Aschenfelter and Kruger twins paper, and the Imbens, Rubens, and Sacerdote study using the lottery to estimate the effects of unearned income. It is in the methodological part of this credibility revolution that the contributions of my work with Joshua Angeris lie. Reading the empirical papers that made use of natural experiments, Josh and I tried to make sense of them and connect them to the then current econometric literature. The problem facing us was that the methodological literature at that time seemed to make a lot of assumptions that, in Leamer's terms, nobody took seriously. There were assumptions about causal effects being the same for everybody, and lots of functional form assumptions. These assumptions did not seem credible, and statisticians analyzing data from randomized experiments were not making them. It seemed to us that fundamentally the credibility of estimates relying on such assumptions could never be as high as that from estimates that did not rely on them. But at that time, we did not really have a good way of expressing our assumptions without writing down models that immediately tie down functional forms. Critical assumptions were traditionally expressed in terms of correlations between residuals and other variables. And to define the residuals, we needed the functional forms. So we were kind of stuck there. Then, reading some of the earlier statistics literature, and in particular Rubens' 1974 paper, where he introduced the potential outcome notation for causal effects in observational studies, made a big impression on me, on both of us. He wrote that to think about a causal effect, you want to think about a unit, say a person, at a particular point in time. And they have two options. They can take a drug, and some outcome will result from that, or they cannot take the drug, and a different outcome will result. And the causal effect is the difference in these, what he called potential outcomes. It tied the causal effect directly to the manipulation, to the action that you could take at a particular moment in time, and in doing so made them relevant for policymakers. And that really resonated with us. It resonated because it was very similar to the way we think about the basic building blocks, the primitives in economics. Things like utility functions, production functions, or demand functions. A production function describes what the output will be as a function of various inputs. Differences in the production function for different bundles of inputs give you the causal effect of the inputs. These seem very similar to us to Rubin's potential outcomes, but while they were widely used in economic theory, they were just beginning to get used again in the econometrics literature at that time. And part of the attraction was that the potential outcomes setup allowed you to estimate causal effects on what seemed to us very clear assumptions. Instead of the traditional assumptions defined in terms of residuals that were themselves defined through functional form restrictions, Rosenbaum and Rubin formulated their critical assumptions regarding the absence of unobserved confounders as conditional independence restrictions of potentially observable variables and the treatment. The focus in the Rosenbaum and Rubin work on research design and assignment mechanisms as a way of building conceptual bridges between observational studies and randomized experiments appealed a lot to us. There seemed a very accessible and transparent way to formulate assumptions, and we wanted to apply those ideas to more traditional econometric settings with unobserved confounders, such as Josh's veteran study. In his thesis, Josh was interested in estimating the effect of veteran status on mortality and earnings, using the draft lottery number as an instrument that did not directly affect the outcome other than through veteran status, using a standard linear instrumental variable setup.
So what we tried to do was bring that same type of clarity we saw in Rubin's work in the unconfoundedness setting to the instrumental variable setup. Let's think about the assignment process in that case. It really has two stages. The first stage is purely about chance. People are randomly assigned to be draft eligible or not. In the second stage, choice comes in. People who are drafted either serve or do not serve, depending on who they are. And similarly, people who are not drafted either serve or do not serve, depending on who they are. Because choice is involved in that stage, we cannot simply compare veterans and non-veterans. To see the problem, it's useful to think about the four possible subpopulations defined by the individual's response to the draft. Some people will always serve in the military, irrespective of whether they get drafted or not. We call those volunteers, or always takers. Some people will never serve in the military, irrespective of whether they get drafted. We call those never takers. Next, there are people who serve if drafted and do not serve if not drafted, the compliers. Finally, there may be people who do the opposite, people who do not serve if drafted, but who volunteer if they don't get drafted. We call those individuals defiers. This is just definitional, but it greatly clarified the problem in our thinking, and we had some help from Gary Chamberlain, our colleague at Harvard at the time, in getting there. Now, if everybody was a complier, we would have a regular randomized experiment and the analysis would be straightforward. We would simply compare drafted and not drafted individuals, and that would be the same as comparing veterans and non-veterans. But it's not quite so simple. Draft status and veteran status were less than perfectly correlated. Using some of the Anger's draft lottery data, we find that among those drafted, only 31% actually served. Among those not drafted, 19% served. So there are non-compliers of various types, and the challenge becomes how to disentangle the mixtures we find in the draft veteran status cells.
To consider this challenge, let us partition the population into four subpopulations by draft and veteran status. Consider one of the cells, individuals not drafted who do not serve. Such individuals can be either never takers or compliers. Which of these two types they are depends on what they would have done had they been drafted, but we cannot know that for sure. Similarly, the second cell, people who were drafted but did not serve, are either never takers or defiers. The third cell, people who were not drafted but served, consists of always takers and defiers. Finally, the last cell, people who were drafted and served, consists of always takers and compliers. Now we make a key assumption, namely that there are no defiers. This, what we call the monotonicity assumption, helps a lot. It means that we know that all individuals in the second cell are never takers. This assumption seems very reasonable in the context of the draft lottery example, where being drafted increases the incentives to serve. And so there's no reason to expect that there are a lot of people who respond perversely to such incentives. In other cases, however, where instrumental variables are used, it's not so plausible. Specifically in what are now called judge leniency designs, where the identity of an administrator, say a judge, is used as an instrument, it need not be the case that someone who's on average more likely to assign individuals to a treatment is weakly more likely to do so for every single individual. Now let us add a second partition of the population by the response in terms of military service to the draft status. That is a partition into the compliance types. Because of the monotonicity assumption, there are only 3 types left: compliers, never takers, and always takers. Using the shares of the 4 groups by veteran status and draft status, in combination with the random allocation of draft status, we can infer the fraction of never takers in the population, namely as the fraction of people who do not serve despite being drafted. In this sample, that is 69%. Similarly, we can infer the fraction of always takers as the fraction of people who serve despite not getting drafted, which is 19%. This leaves 12% compliers. Note that we also know the average outcome in all 4 cells by veteran status and draft status. For example, the cell corresponding to individuals who were drafted and did not serve, and were therefore known to be never takers, have an average for log earnings of 5.40, and analogously for the other 3 cells. This is where the second key assumption comes in to disentangle the mixture. We assume that for never takers, for whom the draft status does not affect their veteran status, we assume that for those never takers, draft status also does not affect the outcome. In other words, what we call the exclusion restriction requires that the instrument, the draft status, does not affect the outcome directly. It affects it only indirectly through its effect on veteran status. Some version of this exclusion restriction underlies all instrumental variables approaches. In many cases, this is the most controversial assumption in the instrumental variables applications, and in many cases one can come up with arguments why it may fail, and one needs to carefully consider this. Now we know the average outcome for never takers. We also know the average outcome for the cell with individuals who were not drafted and who did not serve, a mixture of compliers and never takers, namely 5.45. We can also infer the share of compliers in that cell, 15%, from the marginal shares of the 3 compliance groups. Therefore, we can, under the exclusion restriction, back out the average outcomes for compliers without military service as 5.69. Similarly, we can back out the average outcome for compliers with military service, 5.46. The difference between these 2 averages gives us what Josh and I called the local average treatment effect, here equal to minus 23%. What are the concerns with the local average treatment effect? As people quickly pointed out at the time, the compliers are an unusual subpopulation to focus on. We cannot tell for sure whether any given individual is a complier or not, and so the local average treatment effect is the average effect for a subpopulation that we can only speculate about. However, we can say something about this subpopulation. For starters, we can infer its share in the population. Moreover, we can infer the distribution of their characteristics, for example, how old they are or how educated they are. It is also the only subpopulation for whom we can consistently estimate the average causal effect without additional, often difficult to believe, assumptions. Finally, it is often an interesting subpopulation substantively. In the draft lottery example, it is the people who are encouraged by the draft to serve, and that is clearly an interesting group if we're interested in the implicit tax imposed by the draft. In the Angers-Kruger quarter of birth returns to education paper, it is the individuals who are on the margin of dropping out of school, and their returns to education are of particular interest for policymakers that try to encourage people to stay in school longer. This setup for understanding the role of instrumental variables in estimating treatment effects turned out to be helpful in more general settings, including settings with multivalued or continuous treatments, such as education in the Angers-Kruger quarter of birth paper.
Another example of the local average treatment effect framework is the fish market paper, joined with Josh Angers and Katie Grady, analyzing daily data on prices and quantities of fish traded at the Fulton Fish Market in New York, collected by Katie for her PhD thesis. We were interested in estimating the demand for fish, but like Timberg in 1930, we're cognizant of the fact that prices are not set randomly. To estimate a demand function, we needed an instrument that shifts supply. Katie's idea was to use weather conditions at sea on previous days, or more precisely, wave height and wind speed. If the weather had been bad, with strong winds and high waves, it would have been difficult to catch fish, and as a result, the quantity supplied for any given price would be low. If the weather had been particularly good for catching fish, the quantity supplied at any given price would be relatively high, and at regular days, the quantity supplied would be in between. Now, if we average quantities and prices on bad days, on regular days, and on good days, these three averages will all lie on the average demand function, but they will lie on different supply functions. As a result, they allow us to trace out the demand function. The extension of the local average treatment effect results allows us to precisely describe what the average is we're estimating here and what that tells us about the demand function.
I started this lecture by giving a brief history of causal inference up to the origins of the credibility revolution in the late 80s that motivated our work on methods for causal inference. Since then, the field of causal inference has expanded beyond recognition, with work in many different disciplines, from many different perspectives, and focus on many different policy questions. Let me briefly discuss one of them.
One of the most exciting new ideas in the causal inference literature in social sciences is the synthetic control approach developed by Alberto and Abadi and co-authors. This method is closely related to the difference in differences methods used by Card and Kruger in their minimum wage study and by Card in his Muriel boat lift study. In one of their canonical examples, Abadi, Diamond and Heimmuller are interested in estimating the effect of German unification after the fall of the Berlin Wall on West German gross domestic product. We directly observe West German GDP given the reunification, and so to get the causal effect we just need to estimate the counterfactual value of West German GDP in the absence of the reunification. A traditional approach would have been to look for another country that could serve as a match for West Germany in the absence of reunification. That is hard. Neither Austria or Switzerland or the Netherlands or any other country really would necessarily be a satisfactory match. What Abadi and co-authors did is make the case that a convex combination of some of these other countries, none of which are really a satisfactory match on their own, could be a much better match. This convex combination of the other countries, the synthetic West Germany, is chosen so that its past GDP values match that of the actual past GDP values for West Germany. This method in its various forms is now widely used in empirical work in social sciences, for example to estimate the effect of Brexit on UK GDP or the effect of COVID policies in various states or countries.
Let me end this lecture by acknowledging the influence of my fellow laureates, Josh Angrist and David Card, on my thinking. I had the great fortune of having had both of them at different times as colleagues, Josh at Harvard and David at Berkeley, and have learned a tremendous amount from them. I am honored to be sharing this prize with them, and only wish that Alan Kruger, the only economist who has co-authored with all three of us, could have been here with us. I also wish to acknowledge my debt to my co-authors and students on this journey. One of the greatest benefits of an academic career is the ability to continually get challenged and learn so much from so many great minds. And my students and co-authors have taught me an enormous amount. Finally, I want to thank my family. My parents passed away in the last 4 years, but I was very happy to be able to celebrate the news on October 11th with my wife and many times co-author Susan, and with our incredible kids, Carl, Andrew, and Sylvia. The video of their discussion with me about my work has garnered more views than anything I've ever done. Thank you, guys. Thank you all.